parameterized, cannot change continuously. Now it turns out that the model is integrable. I will show you how you prove that. It's not very difficult. And also there is some Yangian symmetry, which I'm not going to enter at all in this talk. Now, what is very important for my discussion is what I wrote here. The theory has, the action depends on the group element G and two parameters, K and lambda inverse. K is a positive integer. Lambda is between 0 and 1. If you see its definition, it turns out to be between 0 and 1. But you can think of them in the complex plane. And it turns out that the action and whatever you can derive from the action are invariant by a simultaneous inversion of the group element, flipping of the sign of K, and inverting lambda. So that means it's some sort of duality, but in quotation marks, not like the duality we have in string theory, but something that inverts.
Go ahead, and I'll ask the question once you finish.
Okay. It turns out that you relate something for lambda small to something for lambda big, and this in fact will be instrumentally computing certain things. In fact, this relation here should be reflected as a symmetry in all physical quantities that are going to compute, for instance, beta functions, anomalous dimensions. Also, if you embed this to supergravity, that means you turn on Ramon fluxes, as we will see if I have time towards the end of my talk, then it should be invariant under this symmetry.
So then you're saying that there's a symmetry between lambda and lambda inverse. Here you mean the model where there's also a D, right? Like,
yes.
No, not when you consider the limit of lambda.
Okay, I can sketch a little bit this proof. So if you go on this action, you have to change lambda to lambda inverse, flip the sign here, and invert G. If at the same time invert G and flip the sign of K, that means the Wessel-Minor term, the second term in the action, stays the same. However, you change the sign of the kinetic term here. However, it turns out that this will be compensated by a term that will come from here. So, in fact, the fact that this coefficient here is 1 and not 32, it plays a role for the symmetry.
Do you see the spirality before integrating out the wave field?
Say it again? If I will see that.
Do you see the spirality before integrating out the wave field?
I think, no. But I could see it once I integrate it before I plug it into the action. But before I haven't checked it. Okay. Before you do that, you have to take into account how the measure of integration changes from A class minus in the part integral to group elements which parameterize it like this. So you get some extra contribution when you change the measure, etc.
Well, this is the wave field will also change.
The A field, yes. The A field changes. Yeah. But to guess how it changes, you have to integrate and then see how. Now it will depend on G and K and lambda, and see how transformation on K and lambda induces transformation on the gauge field. But if you want to do it before, I'm not sure.
So this is not the symmetry of the Tiering model?
No. I don't know if I wrote it, but if you go in the Tiering model, lambda appears linearly.
Right.
So it cannot be a symmetry of the Tiering model. Okay?
Yeah.
It's a symmetry of the effective action that I just wrote. Now, of course, okay, once I have that, then I give you an example very fast to see that it's not very mysterious. It's not that complicated. If I do it.
So do you treat K and lambda independently?
K and lambda are different parameters.
I mean, because the effective action, lambda was originally dependent on K, right?
Let me write lambda. So being Greek, I use Greek letters. So I have a K, and here I have a kappa square. So this is different than that. So instead of using kappa, which was the overall scale of the principal model, I use lambda, just trade-off of parameters.
Oh, I see.
Okay. So I
instead
had
of kappa. Instead of kappa. you
instead
use-
of kappa, I use lambda. So I started with.
Okay.
Let me show you something. Yes, that's it. So the case. Well, this I don't know. I wrote it from different process, but just one lambda. So I parameterize SU2 in this particular way. There are many ways, but one way is this. So it's nice because given the result, and this is the metric you get, and this is the antisymmetric density you get. If lambda is 0, then this term is 1. This delta becomes 1. This is 1, and you get S3, which in a particular way, written in a particular way. And B is just this term, B, well, this term is 1. B is what you will have for the same B you will have in the Wilson-Witten model. Because when lambda is 0, then we should be in the conformal point. So it's not that complicated. This is the reason I wrote this. Now, let me show you integrability. It's very easy. So, to show integrability, you have to first find the equation of motion of the theory and then see if you can cast it in a Lax pair. So, the equations of motion arise by varying the gauge fields, A plus minus, and the group element G. So, if you vary the group element G, you find this equation, which is equivalent to that. So, this is not independent, just wrote it to see some symmetry. And if you vary the gauge fields, you get these two because you have two gauge fields. And then if you use this and that, you plug this in there, this in there, then you end up with that, which you can think of them as a 2x2 system of equations for this object and that object. So you can solve it like that. So you express the worldsheet derivatives of A plus minus in terms of some commutator and the deformation parameter lambda. Now, the next step is to recall what is very sketchy. The Lax pair formulation, the Lax equation, which is like this. So in the four notation, in the four physics notation, from that you can define the classical monodromy metrics, and you can show that this is 0, this is path order here, this is 0, and it turns out that if I identify L plus minus in this particular way, where mu is the spectral parameter, so it's some complex parameter, and using what I said before, namely this, then I can show that this object obeys this equation, and it turns out that that's enough for classical integrability because I have a spectral parameter I can expand and derive infinite number of conserved currents. Now, as I said, these models I'm presenting here in the simplest case can be generalized to a matrix lambda AB, and it turns out for other matrices, very specific though, we still have integrability, and also this can be extended to coset spaces embedded in some supergroup, which has a bosonic part, ADS 5 versus 5, and this is of course important for ADS CFT. But I'm not going to talk on that. Now, a few more comments about the algebraic structure. If you just use the canonical formalism, and you identify with some scaling the I plus minus proportion, some proportionality constant to these gauge fields, then these obey these Poisson brackets. It turns out that this is the deformation of the current algebra for 3C pi models, which you recover if x, this parameter x goes to 1. Anyway, so we have established integrability, and now I'm going to show you how we compute anomalous dimensions in the data function. So let me sketch how we do things. We have for lambda equals 0 a conformal theory. That means a current algebra. In fact, one for the left movers and one for the right movers, which do not talk to each other. Now, for the left movers, this is the current algebra. I mean, I have scaled things so that this square root of k appears here, so that I keep track of the 1 over k type of expansion. Because I will compute things exactly in lambda, but leading order is 1 over k. Okay? And then I'm supposed to consider correlation functions, which will depend on lambda, and compute this object here. So traditionally, you break down powers of lambda, you do the integrals, you get some infinities, put some cutoff, and as in usual field theory. Okay, so the basic correlation to do this is a 2-point function, easy from here, and a 3-point function, and the rest of the correlators from word identities in usual conformal field theory for current algebras. Now, as I said, if you do that, you have to find the relations between pair and normalized quantities. And it turns out that if you do things up to cubic order in lambda, 3 loops, that means 3 insertions, and you do the integrations. It takes some time, and you have to keep track of order of integration, don't mess it up. There are some subtle issues, but it turns out that this is what you compute. This is what you compute, and CG, just to remind you, I think it appeared in another talk today, it's just the quadratic of Casimir in the adjoint representation. Some positive numbers in the way I define things here. And once you have that, then you can compute the beta function perturbatively. So here I just went up to cubic terms. Here's a negative sign that I think we commented before, and the anomalous dimension, which changes also perturbatively. Now the question is how you compute this exactly in lambda. This was the original, what I wanted to address at the beginning of the talk. Now, so far we just have perturbation theory, but I would like to use now the symmetry that I know it should be behind these models. Now, the symmetry is this one, just to remind you, is flipping the sign of k and inverting lambda. This should be a symmetry of the beta function and also the anomalous dimension. Of course, you might say, can I check it? Yes, you can maybe go even beyond the order of perturbation here. I have computed things, and once I compute something I call exact, I check it. I can check it a few more orders if I want. Now, so the idea is to use the perturbation, the perturbative information that I have obtained, plus the symmetry to get something exact. Now, before that, I have to use also some analyticity arguments, which go as follows. Remember that this action I showed you depends on the group element of the parameter lambda and the overall scale k. Now, if I expand the group element around the identity, so I assume that I introduce some coordinates xa and I take x to 0, so I expand it around the identity, then the action takes this particular form. Now, this form tells me essentially that I should expect in whatever I compute to have poles in the complex plane in lambda 1 and lambda minus 1. So if I make some sort of ansatz for my exact result, I should take this into account. The second piece of information I will introduce is the action, this effective action, has two well-defined limits. Doesn't matter the names, that's the subject of the different talk, but it's a limit where k goes large but lambda becomes 1 in this particular way. So goes to 1 but in this particular way, and also another limit where lambda goes to -1 in this particular way. So that means the beta function and the anomalous dimension should have good limits when I take these particular cases. Now, an extra thing which I'm not presenting here, but a lot of it is already in this limit, is the fact that I should take into account the Calan-Szymanczyk equation for the correlators, and somehow all this behavior lambda should be consistent with that. But this will not be necessary. This I already talked, so I have perturbative information plus this symmetry, and then putting everything together, this is the ansatz for the for the beta function and the anomalous dimension. So I know that I should have for large k some 1 over k factor in front, because this is the overall radius scale in my effective action. Then I should have poles in +1 and -1 as far as lambda is concerned. I don't have the -1 because it turns out that in order to have these two well-defined limits, the exponent for the 1 minus lambda should be 0. And it turns out that the exponent for the anomalous dimension should be 1 and 3. So once I have that, I impose a symmetry, this one, which tells me that these functions f of lambda and g of lambda should obey these relations, which tells me that if I want analyticity in the complex plane everywhere except ±1, these f and g should be polynomials of degree at most 4 in lambda. So that means I have 4 unknown coefficients here and 4 there. But because of this symmetry, there is a relation between the coefficients which restricts the number. And moreover, I have to match this result with the perturbative result that I already have. In fact, up to 2 loops, lambda squared. The coefficient of lambda cubed will be a check. It has to be the same as one computed in perturbation theory. So if I do that, this is what you get. So you get for the beta function this relation, and for the anomalous dimension that. And we have computed that if you expand this and we keep the lambda cubed term, it's the same term that you have computed independently using perturbation theory.
Process. Do you have a independent understanding why the symmetry is quantum mechanical?
Quantum mechanical, okay. Perhaps you are asking something I was wanting to address towards the end. This symmetry is correct in the form I presented for large k. So k is the overall scale. So somehow it's once I have included all lambda correction, as far as k, the overall scale is still classical. So this is all I know so far. But we have a sort of understanding of what would be the symmetry for small k, which I will say something at the end. Now, if you are asking,
But you assume this symmetry basically to derive all these.
yes, I assume that symmetry. I have checked it also. That means
Check out the two.
no, 2 loop is enough to fix it. But then we checked it for lambda cube, the next, and we found the same. So of course you might say it might fail later, but I don't think so, but you are welcome to do. Turns out that these integrals, although they are two-dimensional, they are not that easy to do, because you get infinity, you have to give the order of integration and all that. But we have checked, in some other case, we have checked even the next one. It turns out the coefficients are correct. Okay, I'm not going to spend time for 3-point functions, but this is what you get. So for the 3-point function of the 3 holomorphic currents, of course, for lambda 0, this term goes to 1 over square root of k, and this is what you get from conformity theory. And for lambda 0, of course, anything with holomorphic and anti-holomorphic is 0. But when lambda is not 0, then it's an expression. This is what you get. And also we have computed correlators involving primary fields or mixed correlators, but all these are in the paper, but I think I explained the idea for the currents. Now I have a transparency which probably we could have asked, one of the original motivations is to see if flowing it towards the infrared get a new fixed point. As you see, that's not the case here. But it turns out that if you have different couplings for the left and right movers, and you compensate for the difference with some chiral matter, of course, then you can have a new fixed point when you flow in the infrared, which has to do with the ratio of different levels for left and right movers. But that's if you have some questions later, we can discuss. Now, let me comment a little bit about the gravitational approach. So again, I repeat for convenience the action. This is 2-dimensional sigma model action, and we know from very old work that in the space of all metrics and all symmetric tensors, there should be a running which is driven by the generalized Ricci tensor. Generalized why? Because this means minus means that the connection used to define it contains the B field. Okay, so that means, for instance, it's not symmetric under the interchange of mu and mu. Now, in the mathematical literature, if there are mathematicians here, this is also related to Ricci flows. For instance, mathematicians have studied it. Okay, now, once you have a set of equations like this, you can ask yourself, okay, let's use this particular model, plug it in here, and see if you can absorb, if you can cast everything into something simple, involving only the running of the parameters lambda. Because in principle, this equation tells you that full metric runs. But you make the assumption, and see if it's consistent, that the metric, the form of the metric is the same, but what changes is the way lambda depends on the logarithmic energy scale. Okay, it turns out that if you do this work, it's quite a bit of work, that the beta function we get from field theory, it's the same as the one you get from here. And with some tricks, if you are interested to, I can explain, you can also extract the same anomalous dimensions we had before. Now I come roughly the last 10 minutes or so, the last subject of this talk, which has to do how to embed this into string theory of supergravity. Okay, now of course the model is not conformal, there's a running. So if you don't have Ramon fields, you plug it into the inverse parts part of subtype 2 supergravity, it will not be zero. The equation will not be satisfied, so you need some source terms. And that means you have to know what the Diladon is and possibly other forms. Now the Diladon usually in this business comes from the construction. So remember we had the path integral involving gauge fields A plus A minus. You integrate them out, and in the process of integrating you get some determinant, regularizing it, creates Diladon. And a compact way of writing the Diladon is this, is the determinant of this object here. So lambda minus 1 times the unit matrix minus D matrix transpose that I defined before. Okay, and then you have to support this with Ramon fluxes. Now the rules, personally the way I understand the rules is with the connection of this what is called non-abelian duality, but I'm not going to explain this. I will just list you cases that we know and then give you an example. Now the cases we know is cases which have some interest in string theory. For instance, this first case is the near horizon of the U1 T5 system. This one also has to do with black holes, so it's ADS2 S2 with some 6 toros. And of course, these cases have lots of isometry. Also, this one, well, it's fine, sorry. This one can work out something, but it's quite complicated. So I decided to restrict this case. So I'll give you the results, which are quite explicit for this case.
Sorry, that solution in type 2, which
yes, with type 2.
Type 2
well, for instance, this one I can do type 2A or type 2B, you will see.
And then you do non-abelian duality and
No,
you
non-abelian, forget it. I mentioned it because there's a limit where this can be thought as non-abelian duality. I don't want
duality of something else.
Of ADS2 cross S2. But let's not mix the two talks,
Okay.
but we can discuss later.
Okay.
What I mentioned is the rules to get Ramon fields are what I would have obtained by thinking of it as non-abelian duality. But this is for generic lambda, that means not near 1, which is the limit you have in mind. I don't have the rules, it's more empirical. So I present this case just to see how it looks like. In fact, it reminds of something interesting in the black hole physics in 2 dimensions. So the metric is just using a construction which involves not group spaces but cosets. So you can modify what I said for coset spaces. It's a little bit, some details change, but it's not a drastic, the idea is the same. If you have coset spaces, the perturbation is driven by parafermions instead of current by elements, but the idea is more or less the same. So this is the metric you get. So this is 6 torus, so 4 to 9. Forget this for the moment, although it will be essential in the supergravity construction. And then if lambda is 0, this goes away, and this becomes 1, and then you get, this is just, as you will see, these two cases is the space-time corresponding to the exact conformity theories for these 2 cosets, exact conformity theories. In fact, the first one, if you analytically continue to cover all 2-dimensional space, corresponds to a black hole, which was discovered by Witten in 1991. Now, so one way to think of this is as a deformation in this context, a lambda deformation of the 2-dimensional black hole. Now the diladron is that, and the symmetric tensor vanishes. And now we have to see how to supplement this. If lambda is 0, then that's it, it's solved. You don't need Ramond fluxes. But if lambda is not 0, then you do have to fit some fluxes. Usually when you construct fluxes, it's nice to have some frames. Now the natural frames here are the ones dictated by the form of the action, or of the metric. So I just wrote the first one. No, it doesn't. It turns out it's not a typo.
But you start with L.
It turns out that the lambda depends on the diladrons overall, which I can always scale out. It's not generic in this particular example.
It is true.
Yes, that's what Kostas said is the following. If you have to compute this determinant, somehow you expect some lambda depends in your determinant. But it turns out that for this particular example, the lambda dependence is overall, so I can scale it out. It's just a constant. So, okay, so I have 2 options to embed either in type 2B or type 2A. And these are what happens. For type 2B, for instance, you have to, yes, you have to use, this is where the 6-dimensional space is important, because the 6-dimensional space has a color form and a 3-form holomorphic, which is, you take the real part of that form and you call it J2 and J3. Yes. Okay, and using these 2 objects, you can compute the phi form for type 2B. You don't need anything else, but for type 2A, and F2 and F4. I suspect these 2 cases must be related with the usual duality between the 6 torus. I mean, I don't think they are independent. Okay, so, and as I said, one can think of it as a deformation of this black hole of Witten, which of course was discovered by when lambda is 0. In 91, what the space-time is precisely how the black hole picture is deformed is still unclear. Personally, I haven't worked on that. But I think it's an interesting probably direction from the gravity point of view. And here I have my conclusions. Okay, so what I explained is how to take conformity theories and deform it in a way that preserves integrability with finite parameters, not infinitesimally away from the conformal point. So for lambda, let's say finite. And also how to compute explicitly exact results and not only in principle. To do that, it was very important to have some perturbative information as far as the beta function of the running of the coupling and the anomalous dimension, and to use in a clever way this symmetry that the effective action had. So the results I showed you are exact for any value of the parameter lambda, but for large values to leading order in the overall scale K. Okay, now although I didn't mention, I didn't except for the example, there are Cossette's versions of this story where you have similar results. And in fact, the Cossette versions are the ones that, for obvious reasons, I think, are mostly related to solutions of interest within ADS-CFT. A subject which I did not cover, but for those who have been aware of the related literature, this kind of lambda deformations, although at the beginning it was not obvious, relate to what are called eta deformations, which are basically deformations of the principal Gara model and not of the CFT. In a particular way, if you relate the two solutions with what is called Poisson-Little duality. Poisson-Little duality in a nutshell is a T-duality which relies on an algebraic structure and it doesn't rely on the existence of isometries. Okay? If you are interested, I can explain later. Now, there are several avenues to continue this work. For instance, as I said, what I presented here is exact in lambda, but leading order in K. The question is how you will change the symmetry to include K corrections, or if possible, exact in K. And we think that the correct change of symmetry is instead of K goes to minus K, to go to minus K minus number times the Coxeter number for the group, which is kind of similar in what we have in the Sugawara construction of conformal theories. I don't think immediately this will be possible, so one may rely on large N expansion. N here has to do with the Casimir, the quadratic Casimir of the group, so if it says UN, this of course depends on N. So if N is large, CG, what I was writing, becomes large, and maybe one can do an expansion with that parameter as well. Other cases include something I mentioned briefly, that integrability. We have integrability not only when we have one parameter, but more parameters in specific ways, which are encoded some metrics, and one can also pursue research in that direction as well. So that's all. Thank you.
Very open question. So it's a supersymmetric version of this?
If you just take Killing-Skinner equations, for instance, no, supersymmetry is broken. So it's integrable, but not supersymmetric.
Another open question is rational whole group theory. You can get it from boundary transformation theory.
Yes.
So is that version of this?
Not that I know where you're getting it. You can think of a Quatermain of Witten as a boundary of three-dimensional Chern-Simons, correct? In fact, this has implications of black holes and all that. So you are saying if there is a lambda-deformed Chern-Simons, that's very interesting. I don't know. That's very interesting.
So according to your metric of SU2, there is a preferred U1 subgroup of SU2. Should I, from the physics point of view, what pick a particular subgroup?
Okay, so let's go back to this transparency.
B group is otherwise homogeneous. Why the
Essentially, I think what you're commenting, what you're commenting, let's take lambda 0, so this is 1, this is 1. And then you have an S3 metric where you see explicitly the S2 factor. There are other parameterizations where you see two U1 factors explicit. Why did I choose this one? Is that your question?
No, the question is that in the original model, it seems that there's no preferred subgroup of SU2. But now in the metric, you have a preferred U1 subgroup. So what?
You want this? You mean the subgroup I guessed was the whole SU2?
This metric has a preferred U1 subgroup.
I'm not sure I understand what you're saying. This metric has an S2 written here. There is a U1 inside S2, however.
The U1 is an alpha parameter.
No. It depends on alpha. It's a sine alpha parameter. So this is not an isometry. Shifts of alpha is not an isometry.
So anyway, in this metric, the sphere and the U1 are treated differently.
But then I think I said that there are other parameterizations, also the original group element, which will give you a different form of the metric, but however they are not as simple. So that's why I chose this.
But in your original model, the V group has no preferred splitting of circle and S2. So my question is, what is the physical mechanism that so that on this type of space?
Do you relate this to the fact that I gauge fixed Z tilde to 1?
No.
Okay. Physical, I wouldn't call them physical. I would say that I chose to parameterize the group element in a way that the result looks as simple as possible. I'm not sure you're asking, however, that.
In the original model, the V group is perfectly homogeneous.
Yeah.
Now it is not. So I asked, what is the mechanism?
Well, there is, okay, the mechanism, let's take lambda not zero, but small. Okay? So if that means if it's zero, not zero, but small, it's like the original SU2, S3, plus current carried by linear. That deforms it.
But deforms it in a way that is still homogeneous on the order left of right.
Well, this metric here still has left symmetry corresponding to this S2.
Maybe what you say homogeneous is at lambda equal to 0 is SU2 times SU2, right?
Yes, but for lambda different than 0, just as
you just need one SU2.
Yes.
This is a single copy of SU2.
The original model is also three-dimensional. Okay, but it has left SU2, right SU2. This one has also a group action of SU2 left-right, but the same.
But the resulting metric moreover pick a particular U1 direction inside SU2.
That's why I said if you parameterize differently, I will exhibit different isometries. But this is the simplest.
Well,
You can discuss matrix.
Yes, so I think so the deformation is relevant to the deformation of the bilinear form. So by introducing the kind of principal model.
So I'm sorry, I didn't hear you very well.
So the deformation of the theory is relevant to deformation with the bilinear form.
The deformation is driven by this JJ bar.
Yeah, so the non-semi-simple case, so in a based on recent, so we have the relationship. So this included in the deformation. So
For small lambda, my deformation is precisely that. That deforms JJ bar. This has also metric, symmetric part, and anti-symmetric part. And if you write this down, and if you split it into a symmetric in plus minus and anti-symmetric in plus minus, you will see that it has both metric and anti-symmetric parts. That's why both B and the metric, the first correction is lambda. It's order lambda. Because it can be cast in this particular way.
So G is taken as some arbitrary algebra.
Yeah, Z can be not as you do is in the exam. Can be some semi-simple Lie algebra. It could be G2, SU3, anything. Of course, in embedding to string theory, you need something low enough to accommodate up to 10 dimensions.
Maybe, I think you said it, but a crucial aspect was this lambda to 1 over lambda
Yes.
symmetry. Was it dependent on integrability of the so suppose you want to do a non-integral deformation, where does it go wrong?
So the non-integral deformation will be of different kinds, so I'm not sure.
Like your examples, beta function.
Yes.
Suppose you did a deformation which did not preserve the lambda pair.
Ah,
Where would
you
it
mean
break down?
how, yes, so you say whether or not the fact that it's integrable relates to the symmetry.
Yeah.
Well, I can say that the equations look invariant under lambda 1 over lambda and k minus k, but whether or not I could have cases where I have integrability without the symmetry, that I can imagine.
But the other way around? Have the
Symmetry without integrability. That I don't know. I mean, it seems harder to me. To present exact expressions for the beta function and gamma, the symmetry was important, but I'm sure there will be other occasions where the integrability is important.